In this lecture, I am going to discuss some more numerical example based on sampling theorem. In previous lecture, I have discussed about the sampling theorem. Sampling theorem basically provides you the information about the minimum sampling frequency, which is desirable to reconstruct original signal from the sampled signal. And the minimum sampling frequency will be twice of the maximum frequency component present in the signal. Here fh is the maximum frequency component which is present in the original signal, and fs is the minimum sampling frequency, or this term is also called Nyquist rate. This is also called Nyquist rate. So the minimum sampling frequency which is desirable for any signal for its sampling, so that you can reconstruct the original signal from the sampled signal, will be twice of fh, or you can say will be twice of the maximum frequency component present in the original signal, or you can say continuous time signal. And this statement is called sampling theorem. And here the minimum sampling frequency, which is written here with the term fs, is called Nyquist rate, and reciprocal of this Nyquist rate will be Nyquist interval. So basically, the problem related to the sampling theorem, you will have to calculate Nyquist rate or Nyquist interval. But you must remember, the minimum sampling frequency should be equal to twice of fh. If the sampling frequency is less than this value, or less than twice of fh, then you will get a phenomena termed as aliasing, and aliasing has a severe consequence. So to avoid aliasing, or you can say to get accurate signal from the sampled signal, or for reconstruction of original signal from the sampled signal, the sampling frequency, or the minimum value of sampling frequency, which is also called Nyquist rate, should be equal to twice of the maximum frequency component present in the original signal, or you can say continuous time signal. So in this video, I am going to discuss the numerical example, some more numerical example based on sampling theorem. I have already uploaded one video based on the sampling theorem, and this is the second video for the problem based on sampling theorem. So let us consider the first numerical example. This is Sinc 200T. Here signal xt is Sinc 200T. And in the previous video, I have discussed the signal Sinc signal. Basically, Sinc 200T means it is sine 200 pi t. Just you will have to introduce pi here, divided by 200 pi t. This is the meaning of Sinc 200T. And now you will have to determine sampling frequency, or you can say the minimum sampling frequency for this signal, so that you can reconstruct this original signal from its sampled signal. What will be the minimum value of sampling frequency, or you can say what will be the value of Nyquist rate for this signal. So you can see here, this signal consists one term only, one sinusoidal term, and from this sinusoidal term, you can, here omega is 200 pi. So you can find the frequency of this signal. And the frequency of this signal will be 100 Hertz. And obviously, this signal has only one component. So this will be the highest frequency component which is present in the signal. So the highest frequency component present in this signal is 100 Hertz. And according to the sampling theorem, the minimum sampling frequency or Nyquist rate for this signal will be twice of this. So Nyquist rate will be twice of 100 Hertz. It is 200 Hertz. So this will be the answer. So if the task is to sample this signal, then you must remember your sampling frequency should not be less than 200 Hertz, otherwise you will get aliasing. So to avoid aliasing, to get accurate analog signal from a discrete signal, the minimum value of sampling frequency or Nyquist rate for this particular signal will be 200 Hertz. The sampling frequency can be greater than 200 Hertz, but it cannot be less than 200 Hertz. Otherwise, reconstruction is not possible. So this is the concept of sampling theorem. Sampling theorem basically provides you the information of minimum sampling frequency. Below this frequency, you should avoid the process of sampling. And second example, I am going to consider here. What will happen if you have an idea of sampling frequency of signal xt? Then what will be the sampling frequency of x square t, xqt? I am going to discuss this through a numerical example. So now the second signal is, what will be the sampling frequency of this signal? Just I have multiplied one Sinc signal to the previous signal. Sinc 200 pi t is the previous signal. Sinc 200t is the previous signal. Now I am going to multiply one more Sinc function to this. One more similar Sinc function to this. Or you can say I am going to derive Nyquist rate for x square t. So what will be the Nyquist rate for this signal yt? Let us consider this signal yt, which is x square t. The product of two similar Sinc function. What will be the Nyquist rate for the signal, this signal? So this will be Sinc square 200 pi t. Sorry, Sinc square 200 t, not pi t. And Sinc 200 t means it is sine 200 pi t divided by 200 pi t. This is the meaning of Sinc 200t, and whole square is here because this is Sinc square. So you will have to take a square of this term. Now this will become 1 by 200 pi t square into from the concept of trigonometry, you know, sine square theta is basically 1 minus cos 2 theta by 2. So numerator, which is sine square 200 pi t, sine square theta, you can write it as 1 minus cos 2 theta. Here theta is 200 pi t. So cos 2 theta will be 400 pi t. Divided by 2. So this is the meaning of sine square 200 pi t. You can convert sine square 200 pi t in terms of cos using the basic concept of trigonometry. So you can see in this example, in this signal has two components. One is constant, another is cosine term. And from the cosine term, you will have to find frequency component. So only one cosine term is present here. So this will give you the maximum frequency component present in the signal. Here omega is 400 pi t. Here omega is 400 pi, sorry, not pi t, and which is equal to 2 pi f. And from here, the f will be 200 hertz. And this will be the maximum frequency component present in the signal. So sampling frequency will be twice of this, and this will be 400 hertz. So you can see through this example, if you have an idea of sampling frequency or Nyquist rate of signal xt, which is 200 hertz, then what is the Nyquist rate for x squared t? It become 400 hertz. So as you will multiply the similar term together, its Nyquist rate will increase. Similarly, you can check what will be the Nyquist rate for the signal xqt. You will get 600 hertz. Similarly, you can check what will be the Nyquist rate for the signal x to the power 40. So this type of question basically asked in objective example, a multiple choice question, uh, in which it is given as the sampling frequency of signal xt is, or Nyquist rate for the signal xt is f. Then what will be the next Nyquist rate for x squared t? What will be the Nyquist rate for xqt? So you can analyze what will be, through this example, what will be the Nyquist rate for the signal x squared t if you have an idea of Nyquist rate of xt. Now I am going to consider one more example based on this Sinc function. Now what I am going to do this, just I am going to add these two signal, xt plus yt. xt means Sinc 200t, Sinc 200t, and yt is Sinc square 200t. Then what will happen? Then you will see, you will get same answer, 400 hertz. How can you solve? How can you find Nyquist rate for this signal zt? I have already solved this example here. This is the example where I have added two Sinc signal. One is Sinc 200t and another one is Sinc square 200t. So Sinc t means sine 200 pi t by 200 pi t, and Sinc square 200t means Sinc square 200 pi t by 200 pi t square. So you can write this in terms of cos by using basic concept of trigonometry. This will be 1 minus cos to 400 pi t by 2. And you can see here in this signal has two terms, and you will have to find maximum frequency from this term. And here omega is 400 pi, so f will be 200 pi. And according to sampling theorem, the Nyquist rate will be 400 hertz, which is same as the Nyquist rate of this signal. So such type of thing you can analyze through practice. If you have an idea of Nyquist rate of xt, then what will be the Nyquist rate of x squared t? What will be the Nyquist rate of xqt? Similarly, you can analyze, if you have an idea of Nyquist rate of xt, then what will be the Nyquist rate for xt plus x squared t? What will be the Nyquist rate for xt plus x squared t plus xqt? Such type of problem you can analyze through this Sinc function. What will be the Nyquist rate for such type of signal? Now I am going to discuss one more numerical example based on sampling theorem. In this example, it is given a continuous time signal xt is obtained at output of an ideal low pass filter with cutoff frequency this. So here is a concept. This is an ideal low pass filter, and for ideal low pass filter, cutoff frequency and maximum frequency component present in the signal will be equal to each other, and which is given here 1000 pi. And from this, you can get the value of maximum frequency component fh. This is angular frequency, which is equal to 2 pi f. And from this, you will have to find uh, frequency in hertz, which is 500 hertz here. And according to sampling theorem, the sampling frequency for the reconstruction of original signal should be greater than equal to twice of this, means 1000 hertz. And Nyquist interval, which is reciprocal of fs, which you can write with ts. The ts will be less than equal to 10 to the power minus 3. So this will be the suitable Nyquist interval for the reconstruction of the signal. If you want to reconstruct xt from the sampled signal, the Nyquist interval should be either equal to 10 to the power minus 3 or it should be less than 10 to the power minus 3. So in this example, it has been asked, what will be the Nyquist interval? What will be the suitable Nyquist interval so that you can reconstruct, you can recover the original signal from the sampled signal. So the suitable interval is either 10 to the power minus 3 or less than 10 to the power minus 3. So option A and option C has satisfied the condition, because in these two options, sampling interval or Nyquist interval is less than 10 to the power minus 3. So these two will be the correct answer, and this is incorrect answer. So answer for this question is A and C, both are correct. In next video, I will discuss some more numerical example based on again on sampling theorem, but that will be the last video related to the problem based on the sampling theorem.